Core Concepts for Open Architecture AV Design. Chapter 3. Dante Basics. The learning objectives for this chapter are: define various concepts related to network digital audio, including sample rate, bit depth, and bandwidth. Explore the features of Dante audio networks and their use with Symetrix DSP-based systems. Understand Unicast and Multicast modes for audio over IP networks. Explain what the clock is and why it is critical to proper functioning of a networked digital audio system. Recognize the role and impact of latency options. Explain what Dante controller is and how it is useful for troubleshooting. This chapter covers background information about Audinate, information about the Dante technology and hardware, and a top-level overview of how Dante integrates with Symetrix hardware. Audinate, the developer of Dante technology, is headquartered in Sydney, Australia. Dante is developed by network engineers to provide a 100% interoperability solution for all manufacturers using Dante technology. Dante works with most existing networking hardware and does not need specialized network hardware. Dante is an uncompressed, multi-channel digital media networking technology with near zero latency and synchronization. Dante does away with heavy, expensive analog or multi-core cabling, replacing it with low-cost, easily available Cat5e and higher Ethernet or fiber optic cable for a simple, lightweight, and economical solution. Dante integrates media and control for an entire audio system over a single, standard IP network. In 2007, Symetrix recognized the need for a standardized high-performance digital audio networking protocol, not only for our own products but for the pro audio industry at large. After considerable research, we aligned with Audinate to become one of the earliest licensees of the Dante protocol. Since the introduction of our first Dante-enabled product in 2012, we've leveraged the benefits of the protocol for our own box-to-box audio networking, as well as for peer-to-peer connection with major third parties including Yamaha, Shure, and Audio-Technica. Audinate makes hardware modules, development tools, and software products. Some software products are Dante Controller, Dante Virtual Sound Card, and Dante Via. The two main Dante hardware products manufactured by Audinate are the Brooklyn 3 card and the Ultimo chip. The Brooklyn 3 card supports a gigabit Ethernet switch chipset and is capable of up to 64 transmit and 64 receive channels of Dante networked audio. Brooklyn 3 also offers its own high-resolution, low-jitter clocking or connects to an external clock. It also integrates with industry-standard sample rates 44.1, 48, 88.2, 96, 176.4, and 192 kHz. Symetrix uses the Brooklyn series card in many DSP products. The Dante Ultimo chip is capable of up to 4 transmit and 4 receive channels of Dante networked audio. Ultimo has a tiny footprint, but packs a solid punch, delivering up to 4x4 channels at 44.1 and 48 kHz. or 2x2 channels at 88.2 and 96 kHz. Symetrix uses the Ultimo chip for some of our expander units. When converting analog audio into digital, the analog signal is sampled at constant intervals of time. At each interval, the amplitude of the analog signal is captured and then represented as a number. This method produces a stream of values in time and is known as pulse code modulation, or PCM. This is the most common format for digital audio. PCM audio is uncompressed by definition. The sample rate is how fast the audio samples are being taken. If the analog audio samples are taken at least 2 times the maximum analog audio frequency to be captured, the entire audio signal can be successfully recreated. Human hearing ranges from 20 Hz to 20 kHz, which indicates that a sample rate of 40 kHz is sufficient. However, this rate is generally pushed up to 44.1 kHz, the standard value of most CDs, or to 48 kHz, which is the most common value in pro audio. Higher sample rates allow for higher frequencies to be captured. Different sample rates can coexist on the same Dante network. 44.1 kHz, 48 kHz, and even 96 kHz can share the same network. However, devices running at different sample rates cannot share audio. Dante controller does not allow subscriptions to be made if the sample rates do not match. Bit depth is the number of bits of information in each sample, and it directly corresponds to the resolution of each sample. The higher the number of bits, the more accurate and more information is in each sample. Different bit depths also provide a different amount of dynamic range. 8-bit provides a dynamic range of 48 dB. 16-bit provides a dynamic range of 96 dB. 24-bit provides a range of 144 dB. And 32-bit provides 192 dB of dynamic range. CDs are generally 16 bits, 44.1 kHz, while most Pro audio is generally 24 bits. Symetrix DSPs are natively at 24-bit, 48 kHz. Some Dante devices are adjustable to 16-bit, 24-bit, or 32-bit, while others, like Symetrix DSPs, are locked at 24-bit. 32 and 24-bit depths can coexist on the same network and share audio. If a 24-bit device transmits to a 32-bit device, 8 bits are added to each sample. If a 32-bit device transmits to a 24-bit device, the last 8 bits are simply removed. Bandwidth is the amount of data required per second for digital audio. Increasing the bit depth and sample rate increases the fidelity of a system with more data per second being captured. Increased bit depth and sample rate also increases the amount of bandwidth required to transmit the signal. A higher sample rate means more samples per second, and a higher bit depth means that each sample holds more information, making it that much larger. When discussing pure digital audio, not network digital audio, which is calculated differently although related, one channel of audio bandwidth equals sample rate times bit depth. For example, a common Pro audio setup with a 48 kHz sample rate, 24-bit depth, 48,000 times 24 equals 1.152 megabits per second per channel. So, 64 channels of audio at 48 kHz 24-bit equals 74 megabits per second. This same formula can be used for multiple channels of digital audio. In this example, 32 channels with a sample rate of 48 kHz and 24-bit equals 37 megabits per second, rounded up. Transmitting 32 channels using 32-bit instead of 24-bit, the bandwidth increases from 37 megabits per second to 50 megabits per second, rounded up. Most gigabit Dante networks have headroom for 32-bit depth. With Dante, the bandwidth calculation is different, as multiple channels of audio are efficiently packaged into buses. They don't have a one-to-one correspondence with the bandwidth required for a single channel of audio. A single Dante bus of 1 to 4 channels, also called a flow, with a sample rate of 48 kHz at 24-bit uses 6 megabits per second of bandwidth. This can help simplify the math. Presuming the 48 kHz sample rate and 24-bit resolution, 32 channels divided by 4 channels per flow equals 8 total flows. Then, 8 flows multiplied by 6 megabits per second equals 48 megabits per second. The amount of bandwidth each device transmits and receives across the Dante network can be monitored using Audinate's Dante controller. For efficiency, Dante organizes audio channels into groups called flows. One Unicast flow carries up to 4 channels, while one multicast flow carries up to 8 channels. Symetrix can support a maximum of 32 buses or flows for each DSP. This is approximately 320 megabits per second of data at 24-bit. The number of flows per device can be viewed with Dante controller or from Composer's network I/O manager. Whether a DSP is sending 1 channel or 4 channels of audio, this uses one Unicast flow. If a DSP is sending 5 channels of audio, that 5th channel creates a second Dante Unicast flow. The 64 by 64 channels, or 32 buses, available for each Symetrix DSP can be configured in various ways. A few examples of what can be accomplished with 32 buses or 64 channels are: transmit and receive up to 4 channels to 32 different devices. Transmit and receive up to 8 channels to 16 different devices. transmit and receive up to 16 channels to 8 different devices, or transmit and receive up to 32 channels to 4 different devices. There are 2 types of Dante buses. By default, Dante buses are unicast. Unicast buses transmit and receive Dante audio to specific devices. This is a point-to-point type of connection between the devices and can help preserve network bandwidth. Unicast flows carry up to 4 channels of audio. Dante buses can also be transmitted and received across the Dante network using multicast buses. Multicast carries up to 8 channels of audio. Multicast buses transmit the same audio signal to every subscribed Dante device on the network. Use multicast when sending the same audio signal to 3 or more devices at the same time, or when transmitting multiple channels of audio from a console to multiple devices. This example uses a Yamaha QL console to transmit 32 channels of Dante audio to 3 radius and 2 X-out 12s. Dante can be used to perform a digital split from any Symetrix DSP. This example shows a Prism 4x4 sending 16 channels of Dante audio to 8 different Dante devices. When transmitting or receiving audio from Dante Virtual Sound Card to 2 or more Dante devices, it is recommended that multicast is used. Dante Virtual Sound Card can transmit 64 and receive 64 channels of audio. To transmit 64 channels to 2 DSPs, multicast is required. Multicast buses can be created from the properties window of any transmit bus in Composer. They can also be created in Dante Controller. All connections made via Dante Controller may be lost when a system reboots, but connections made via Composer stay synced upon reboot. Unicast sends audio to specific Dante devices. This is recommended when sending the same audio to fewer than 3 devices. Multicast sends the same audio to every subscribed device on the Dante network. Multicast is recommended when sending the same audio to more than 3 devices. The clock determines how the data is interpreted in a digital audio system and determines where in the data an audio sample begins. The clock must be consistent for all devices in a digital system so that it is read the same way. Digital systems rely on a single clock leader for multi-device systems. Dante does not use time division multiplexing or TDM. TDM is used by digital audio transports such as AES, EBU, MADI, and EtherSound. With TDM, each audio channel sends data during a set time interval, and the clock signal is derived from the timing of the audio data. Digital distortion or jitter is caused by inconsistent word clock. The samples are no longer played out exactly when they are supposed to be. In TDM systems, the word clock is embedded in the audio signal and must be unpacked from the data stream. This can contribute to misalignment in some conditions, such as many devices being connected together. The classic solution to remedy this was to use an expensive external clock that would lead each device and force clock alignment. Dante uses a highly accurate clock synchronization method that ensures jitter-free performance for any number of connected devices, without the need for any external clock source. This synchronization method is called Precision Time Protocol, or PTP. Synchronization packets are separate from audio data, and sync occurs at fixed time intervals without jitter. If a clock packet is not received on time, there will be dropouts in audio. Green Ethernet, or Energy-Efficient Ethernet, also known as EEE, is not compatible with Dante. Green Ethernet is a network switch protocol that opens and closes ports based on traffic to save on energy. The millisecond it takes the switch to open a port prevents the Dante clock from arriving at its destination on time and results in dropouts of audio or unintended latency. Dante uses a leader and follower concept with strictly one leader only. The leader is automatically selected based on the following criteria, in this priority order. Is there an external clock? Is there a preferred leader selected? Which has the highest clock quality? And which has the lowest MAC address? After a leader device is selected, it transmits a multicast signal to each follower to keep them in sync. Each follower determines the time offset caused by transmission delay. The follower sends a delay request to its leader. Then the leader replies with a time-stamped delay response message. Next, the follower time aligns itself to the leader, and all followers will be in sync. The sync is checked thousands of times every second. If the leader clock gets disconnected, all followers continue to run from their own clocks, so audio continues. A new leader is then automatically elected and everything syncs again, with no silence and no glitch. Dante takes more time to travel through a switch than a wire. The switch analyzes, copies, filters, splits, and forwards the data. More switches in a network means more latency. Some Dante devices have switches built in to allow for simple daisy chain connections. Many Symetrix DSPs have built-in switches. In this example, the Dante ports are daisy chained from primary to secondary, and the Dante network has been bridged to the Ethernet network. The Dante network can be viewed with a PC via Dante controller and be online with Composer at the same time, without using an external switch. Most Dante devices have a fixed number of latency options. The default setting in Composer is 1 millisecond. Each setting has a recommendation depending on the number of switches. Many variables are considered when choosing the latency setting. In this example, 3 internal switches are used in a daisy chain configuration. This system uses a 0.25 millisecond latency setting. In this example of a star configuration, a 0.25 millisecond setting is also used. This system has 4 Dante devices, but the audio only passes through 3 switches if you count the DSPs. In this example, there is a combination of 5 Dante devices and 2 external switches in a star configuration. Any audio transmitted or received from the console travels through 4 switches. A 0.5 millisecond latency setting would be recommended for this system. Different latencies can coexist on the same network. In this example, the system is configured for 2 different modes, an auto mix mode and manual mix mode. The auto mixing latency is set low. The radius, DVS, and Rios on stage are set at 0.25 milliseconds, and the manual mix at front of house console is set to 0.5 milliseconds. The Rios and DVS transmit unicast with 0.25 milliseconds latency to the radius. And at the same time, the Rios and DVS transmit unicast with 0.5 milliseconds latency to the front of house console. If the Dante latency setting is set too low, or if the network latency exceeds the Dante latency, no audio passes. Dante subscriptions can be made, but no audio passes. Dante controller can be used to monitor the latency between devices on a Dante network, which is very useful when troubleshooting. Here are some Dante latency rules to consider. 1. If the transmitting device and the receiving device have different latency settings, the higher setting is used. 2. Multicast transmission always has latency of 1 millisecond, regardless of the setting. 3. 1 millisecond setting can cover a network up to 10 switches wide. QoS, or quality of service, is network traffic management. Network traffic has different priorities. QoS is used to set the different priorities of the traffic, optimize the network, and lower latency. QoS is only needed when a Dante network is shared with other network traffic. It is also recommended if 100 megabit network equipment is used. The method Dante uses is diffserv, also known as Differentiated Services Code Point or DSCP. DSCP can prioritize 64 different types of data. However, with Dante, only 4 types of data are used. When setting the priority for the data, the higher or larger the number, the higher the priority. The Dante QoS settings, in order of priority, are PTP data that contains the clock timing, number 56. Audio data at 46. All other Dante-specific data, including control and monitoring, 8, is set to a medium priority. And all other traffic on the network is set to low priority, or what's known as best effort. Here is an example of what QoS settings might look like inside a switch. This example uses a Cisco CBS 250. IGMP stands for Internet Group Management Protocol. IGMP snooping manages multicast traffic, making sure traffic only gets to the intended destination. It is used on a Dante network transmitting or receiving multicast audio. IGMP snooping only sends the multicast data to a device that requests the data. This reduces the multicast traffic on the network. When IGMP snooping is enabled, all switches must have it enabled, but one must be set as the IGMP querier. Here is an example of how IGMP snooping works. Dante Virtual Sound Card is used to send test audio to the radius and console using multicast. Without IGMP snooping, the multicast traffic runs throughout the Dante network. When IGMP snooping is enabled, because the RIOs are not requesting any audio data, they will not receive it. The transmit and receive ports of each Dante device are monitored using Dante Controller. Without using IGMP snooping, the RIO in this example is receiving 181 megabits per second. With IGMP snooping enabled, the receive bandwidth drops to 68 megabits per second. IGMP is very effective, especially when there are 100 megabits per second devices on the same network with multicast traffic. A PHY Dante device does not have an internal switch, so the Ethernet jack is connected directly to the Dante Ethernet physical transceiver or PHY, as opposed to through a switch. This includes many Ultimo-based devices on the market as well as Prism DSPs. When a PHY device is directly connected to another PHY device, audio glitches may occur due to PTP sync loss. This is because there is no way to prioritize the PTP clock information as would be possible with a switch. When connecting a PHY device to another PHY device, an external switch is recommended. A PoE injector is a pass-through device and does not resolve the PTP sync loss. In summary, when converting analog audio into digital, sample rate is how fast the audio samples are being taken. Bit depth is the number of bits of information in each sample, and it directly corresponds to the resolution or quality of each sample. Bandwidth is the amount of data required per second for digital audio to traverse a network. Dante works with most existing networking hardware and does not require specialized network hardware. For efficiency, Dante organizes audio channels into groups called flows. One unicast flow carries up to 4 channels. One multicast flow carries up to 8 channels. Unicast sends audio to specific Dante devices. Multicast sends the same audio to every subscribed device on the Dante network. The clock determines how the data is interpreted in a digital audio system. The clock determines where in the data an audio sample begins. Green Ethernet or energy-efficient Ethernet, also known as EEE, is not compatible with Dante. Most Dante devices have a fixed number of latency options. The default setting in Composer is 1 millisecond. If the latency setting is set too low, or if the network latency exceeds the available latency, no audio passes. Dante Controller can be used to monitor the latency between devices on a Dante network, which is very useful when troubleshooting. IGMP snooping is a form of multicast traffic management. It should only be used on a Dante network transmitting or receiving multicast audio. When connecting a PHY device to another PHY device, an external switch should be used.